Hello everyone. Today I'm going to take you on a journey deep underneath the Hawaiian Islands of the Pacific Ocean in search of the mysterious X-discontinuity. I'm going to use seismic waves to uncover a treasure trove of silica that lies down there, which has implications for the heterogeneous nature of mantle plumes and the recycling of material in the mantle. My name is Kemp. I'm a PhD student at the University of Oxford in the UK. And this talk is based on the work that I did when I used to study and work at the University of Cambridge, also in the UK. I worked alongside my supervisors, Jenkins and Cottaar, our geochemical correspondent, John Maclennan, and also I'll be showing some work of Pugh, who's a current PhD student there, who has been carrying on this work, so I've got a bit of a hint of what he does. So without further ado, here is X marks the spot, seismic signals of silica and hidden Hawaiian heterogeneities. The Hawaiian island chain in the middle of the Pacific Ocean is a well-studied example of hotspot volcanism caused by an underlying upwelling mantle plume. This mantle plume has been viewed in various tomographic models both on a global and a regional scale. But there are many questions about this plume, whether it's just hotter than its surroundings, it's got a higher temperature, whether it's got a different composition to its surroundings, or where it's a bit of both. To find out about the variable temperature and composition of plumes, we can use seismic discontinuities. These are sudden changes in seismic wave speed which are caused by phase transitions in minerals in the mantle. They can be indicators of temperature and compositional changes. We can see some seismic discontinuities across the whole world, such as those at the Mantle transition zone at 410 and 660 kilometres depth. These are thought to be due to the olivine phase transitions, which of course is a very plentiful mineral in the mantle. Because of the thermodynamic properties of these phase transitions, if a hot plume goes through the mantle transition zone, the 410 will go down, the 660 will go up, and therefore you'll have a thin mantle transition zone. So if you spot this thinning, then perhaps that is the position of the plume at depth. However, there is actually a garnet phase transition that also happens around 660 kilometres. And this has a different thermodynamic property, and it goes down in hot regions. So if you spot it going down as well as up, perhaps there is an increase in garnet in area. There are other seismic discontinuities that are only seen in patches around the world, such as the X-discontinuity, which is found about 300 to 350 kilometres depth. There are various reasons why this could occur. One of them is that it's a phase transition from coesite to stishovite, which is a form of silica. So perhaps if you see the X-discontinuity, it could mean that there is an increase in silica in that region. To measure these seismic discontinuities, we're going to need some seismic waves, and to detect these we used over 70 seismic stations across the Hawaiian Islands. We then downloaded over 10,000 traces of earthquakes over the last 30 years of quite a high magnitude, and they were all within teleseismic distances from those Hawaiian Island stations. We use this data to generate receiver functions, which can pick out conversions of P waves to S waves at discontinuities. For example, a direct P wave, which is a P wave throughout all of its journey, will arrive first at a station, and then a bit later there will be a P to S converted phase, because it will start as a P, hit the discontinuity and turn into an S wave, and the S wave travels a bit slower, so it will arrive a bit later. And these phases are very small in amplitude, so we need to stack lots of them together to be able to detect them. We therefore produced all these receiver functions from all the traces. We did a big quality check, which removes over 90% of them. So we're left with a data set of about 5,000 very high quality receiver functions. We then convert them from time to depth using a variety of seismic velocity models. And that means that if you see a little red peak at a certain depth, that could mean that there is a conversion happening at that depth and therefore a seismic discontinuity at that depth. We took all of these receiver functions and stacked them in a variety of ways, making depth stacks to detect those conversions. We used some slowness stacking to check whether they were true conversions or whether they were multiples that came in at a similar time. We then use synthetic stacks to try and work out what the geochemical signals are in the deep. And then we finally did a geodynamic interpretation of what was going on and what this could mean for the recycling of material in the mantle. Let's start in the mantle transition zone, at the deepest part of our observational area. We can look at the transition zone thickness over the Hawaiian region, and you can see here the redder parts show the transition zone when it's thinnest. And the thinnest part is sort of to the southwest of the big Hawaiian island, which we've marked with a yellow star. We think that this is the position of the plume because the thinnest part of a transition zone is usually where the hottest region is. If we then look at these cross-sectional depth stacks, so you can see depth on the y-axis, then cut across the Hawaiian region, and the red peaks are showing possible points of conversion and therefore possible seismic discontinuities. The green arrows show that where the thinnest mantle transition zone is, the 660 also splits. You have the upper one, which we think is the olivine controlled one, which is higher because it's hotter, but you also have a slightly weaker lower signal which descends a bit in this hotter region. We think this could be because of the presence of a garnet composition, which will give that different phase transition. We also see in the upper bit of the mantle, especially to the east of the region, you can see a very strong signal at around 340 kilometers depth and a weaker signal at around 410 kilometers depth. This strong signal at around 340 kilometers depth is seen throughout the whole region, and it's particularly strong, as I said, in the east of the region. We made a depth stack of around 600 of the receiver functions in that area. As you can see here, with depth on the y-axis and the relative amplitude relative to P, the direct P wave at the top here on the x-axis. You see that strong 340 signal, and then the weaker 410, and then the strong 660 at the base of the mantle transition zone. Therefore, the 340 kilometer signal is possibly the X-discontinuity, as it's very similar to those seen in other studies. But to confirm this, we used a slowness stack. This slowness stack showed the required slowness for the 340 converted foot wave, but it also showed one of a multiple that bounced off the surface back down to the 340 discontinuity and then bounced back up to the surface as an S wave. So we think from both of these sightings that this is a true conversion and that this is the X discontinuity. We found the X discontinuity, but what does that mean? Well, the X discontinuity is thought to occur because of a phase transition from coesite to stishovite. This is quite a big jump in seismic wave speed, so you don't need that much silica to make it happen, but normal pyrolytic mantle composition doesn't have any of this free silica, so perhaps there is another component in the plume, something like basalt, or at that depth it would be called eclogite. To test this out, we made some synthetic stacks. So we made the same depth and slowness stacks that I've showed before, but this time using various computational models and changing the amount of basalt in the system compared to pyrolite. So we increase the basalt fraction from left to right. This is again a depth stack with depth on the y-axis. And as you can see, as the basalt fraction increases, the 410 kilometer discontinuity, which is in the east region, which this is specifically from, is at around 450 kilometers. It gets weaker and weaker as the basalt fraction increases, whereas the 340 kilometer discontinuity gets bigger and bigger in amplitude. We think that to have this very weak 410 and the observation of the X discontinuity, we need a basalt fraction of around 60 to 70%, which is quite a lot. And geodynamic models show that plumes can only hold about 20% fraction of basalt. So what's going on? Let's look at the geodynamics. Here is a schematic diagram of what we think is going on underneath Hawaii. Let's start at the base. So we see the plume coming up with eclogite entrained within it, and because it's very hot, it's able to carry about 20% of it as eclogite. It then hits the bottom of the mantle transition zone, and we see this splitting of the 660 kilometre discontinuity. The lower one is thought to be because of garnet, and in fact, if you have an eclogite component, then there's probably going to be more garnet in that, which is another reason why we think that there's eclogite here. And then the upper one is because of that olivine, the normal pyrolytic mantle compositional mineral, which gives you that thin mantle transition zone, pointing us towards the southwest of the region being the position of the plume. We then travel up through the 410 kilometre discontinuity out of the mantle transition zone and into the upper mantle. At this point, eclogite is going to become negatively buoyant and start to pool downwards, and we think that this means some of the eclogite is segregated and forms a deep eclogite pool out to the east, and this pooling would increase the amount of eclogite up to percentages of 60 to 70%, giving us those observations that we see of the strong X-discontinuity and the 410 disappearing. The plume then continues its journey up to the surface, melting as it goes, and when it gets up to the surface produces various basalts and lavas. One question is, where is all of this coming from? What is the source of this eclogite? One hint may be that the island basalts that we see at the surface, some of them have some recycled oceanic crust component in it. Perhaps it's from there. Finally, we come to Stephen Pugh's work, who has searched across the whole of the world for the X-discontinuity in various different places, and he has found it. You can see on the left in this green square the Hawaiian observation that I made, and then you can also see lots of robust signals of the X-discontinuity in green. These are mostly at hotspot locations and therefore possibly linked to mantle plumes. You also see some null observations, those in red, which are underneath cratonic regions. So we think that the X-discontinuity is often associated with these hotspots and therefore mantle plumes, and they also seem to be associated in some way with the large low velocity provinces, so those big red blobs around this map. And this suggests that all of these plumes are sampling some source of recycled oceanic basalt, perhaps brought down by subducted slabs, and bringing it back to the surface. And this is in some way related to these LLVPs. You can read more about Stephen's work at his poster on Friday. And so we come to the end of our journey underneath Hawaii. And what have we found? Well, we've seen that to the southwest of the Big Island, there's the position of the plume at 660 kilometres depth. We see that because of the thinning mantle transition zone. We see that the 660 discontinuity splits, suggesting some kind of garnet component in the system, which could be part of a bigger eclogite component, which is further backed up by the finding of the X-discontinuity, which is possibly caused by a silica phase transition. This X-discontinuity is observed in other hotspot regions around the world and suggests that these plumes are sampling some source of recycled basalt, perhaps oceanic crustal basalt, and this is in some way linked to the large low velocity provinces. Thanks very much for listening. I hope you've enjoyed it. If you have any questions, please email me. I'll come along to the session where I'll be having a short talk on this. And if you want to read a bit further, you can look at the paper we published last year, or you can look at the further work that Stephen Pugh has been doing in his poster session on Friday. Thanks very much.